So I already have my first speaker here. Without further ado, I would like to give you the stage. What would you be talking about?
Computational imaging.
I think it's working. So,
This is my talk.
perfect.
Talking about computational imaging for shared
Yes? Please start. Go ahead. The stage is yours.
In there, what I would like to talk about now is give me one slide about our company, what we are doing. And then I would like to talk about computational imaging, what can be done with it. And since we are in the session embedded, I also would like to talk about efficiency. And I will give a forecast on our R&D projects. So one slide regarding our company. MST Vision is a small company. We are like 10 people. And we are not a system integrator, and we are not a camera manufacturer, and not a distributor. We are a development service provider. So we provide services to our customers and technologies. Technologies, I will show you in the next slides what we offer to our customers. In terms of services, we use powerful tools. One of the most important one is Helkon from MVTech. You see them here on the booth. And the second important tool is Visual Applets from Basler, which we use to do high-speed and low-latency applications. And beside that, we do much more feasibility studies, illumination setups, trainings, especially training on Helkon and line scan cameras. To make the slide short, we just provide customized high-end technologies to developers. So we are developers, and we provide developers. So start with the topic, computational imaging. So we just start with a quote from Wikipedia, like many people are doing it when they're doing their thesis. So computational imaging is the process of indirectly forming images from measurements using algorithms that rely on a significant amount of computing. And if you check like the internet, what is computational imaging, the first you hit is always photometric stereo, also known as shape from shading. You see many other applications like multispectral imaging, ultra-resolution color, HDR, so high dynamic range, EDOF, extended depth of field, and I also add deflectometry. And MST Vision, we do a lot on high speed, and we love line scan cameras, so I need to explain one of our core technologies, which we name multi-channel, or others call it multi-cycle, multi-flash. It's different brand names. Same story, we just do time division multiplexing of line scan illuminations. So your object passes only one single time under the camera, and we flash very fast through the line scan lights, and then you obtain up to 8 different images based on standard hardware, standard software, out-of-the-shelf components, covering Quarks Express or CameraLink full bandwidth. Starting with the first application, multispectral imaging. Many people are talking about hyperspectral imaging. So you use a hyperspectral system and you obtain very detailed spectral information for each pixel. And then you classify material to certain bands you can decide. But for many applications, hyperspectral imaging is still too slow. It's getting faster and faster and faster, but sometimes it's still too slow. And if you are lucky and you find an LED that illuminates at the wavelength range that you need, and you can trigger it fast, you just use 1, 2, 3, 4 of these different LEDs. You trigger it very fast using our multi-channel technology, and then you can acquire the multispectral images at the order of 1 or 2 magnitudes more speed, 10, 100 times more pixels per second. And then you may choose standard software to classify the material. And talking about the photometric stereo, it's quite old, invented or published 40 years ago by a guy named Woodham. And the killer application, when it was entering our market, was like the Braille dot, the embossed Braille dot printing on pharmaceutical packages. It's the text for the blind people. It needs to be checked 100%, so it's a high volume application. And as you see in the left image taken by your cell phone, in standard diffusive light, it's quite difficult to see the Braille dot, and to you get mixed up with the maybe complex print on the surface. And Woodham introduced photometric stereo, so you need 3 or more images of the same scenery with 3 or more independent illumination directions. And when you have these 3 or 4 images, based on the images, you can calculate the so-called albedo image, which is like the texture, the print. And you can calculate the surface normal vector, which you may use to calculate mean curvature or x and y deviation. And as you see on the right image, very easy to see the Preil dot. Again, it's an old application. And again, at MST Vision, we love line scan cameras. So we do photometric stereo on line scan. You need a special light for that one, like MTD is offering it, MTD Lights, a manufacturer of line lights. You need an oblique beam. So the light is tilted, and you need 4 of these lights, 2 in front and 2 after the line scan camera, and you rotate each of them by 180 degrees, so you obtain 4 independent illumination directions to have the shade from shading image or photometric stereo image. We did this already 6 years ago at Hochschule Darmstadt because I teach at university also, and this is a demo setup in the lab in the Hochschule Darmstadt. So we have been able to acquire the images needed for photometric stereo at very high speed. The problem was the CPU is by far not fast enough to process fully continuous images coming from the camera. So, and what did we do at MST Vision? We do FPGA programming using visual applets. So we moved the complete algorithm into the FPGA, which is available anyway in your system. And we can do quite cool applications. And just to attract your interest, we play a short game. So I will show you on this slide an image to show the power. It's a print of paper, and we printed our logo on the paper. And let's assume you are sensitive to contamination because maybe it's a food package and you are very scared about contamination, or for sure your customer is scared about contamination. And on the logo of the print, we also added 3 insects as a contamination, and to make it more difficult, we printed the images of the insects. Here you see the image, and now please take 10 seconds time to make sure that you find this real one and all the fake ones. Are you ready to go? Is anyone sure which is the real one and which is the fake one? If someone is sure, raise your hand. Okay, no hand. But if you go to photometric stereo and we use the curvature image, now I think you see them. Yeah. So that shows the power. So our strategy at MST Vision is we move the complexity into the frame grabber. So the image acquisition is much more complex than the normal image. But the software complexity is so easy. That's the strategy, because in the lower image, it's so easy to separate the undesired contamination from the desired print. And using this technology, we do quite cool application. Like one of the killer application is lithium-ion battery. Yeah, so we use this technology on that one. Yeah, so top left, you see the image taken by the cell phone again. And using our multi-channel technology, we can acquire reflective channel, we can acquire a backlight to check for pinholes, we can acquire a dark field image to look for scratches, and we can acquire the 4 images needed for photometric stereo. And based on the lower or the middle 4 images, we calculate the lower 4 images, the curvature image, the X gradient, the Y gradient, and the albedo image. And it's very tough to have this high dynamic range of the shiny part and the very black part. And in the lower images, you see the wrinkles in the material, they come up even in the bright and in the dark area. That's the power of photometric stereo, done with line scans at full speed without CPU load. And it's one of the future hype applications. Everyone wants to enter this market because there are billions of euros invested in this market. E-mobility is a top topic. Yeah. So second one we are in, it's also quite an interesting application. It's the bipolar plate for fuel cells. And I'm so happy that I'm allowed to show this sample because it was very tough to find a sample which we are allowed to show here, because all our customers didn't allow it to do. So thanks to the Fraunhofer IWS, they gave us one of their samples. So top left again, you see the cell phone picture, then the reflective channel, you see a backlight where you can see the cutouts, a dark field for scratches, then again the 4 images needed for photometric stereo, and then the lower part, the calculated images inside the FPGA. And again, without CPU load, all done in the FrankRubber you have anyway in your system, and it's quite efficient. The FrankRubber has only like 14 watts. Talking about efficiency, when we introduced this technology in 2018, it was a bachelor thesis from Simon Wettstein. He even implemented photometric stereo C++ in the CPU, in OpenCL in the GPU, and he did it in the FPGA at that time in the most recent Basler FrankRubber. And then we checked how much pixel per second we can process in terms of bandwidth, and then we also checked how much power these devices need, and then we calculated this efficiency. Yeah? How many megapixels per second and what we can process. And then you see the efficiency of the FPGA. Data is old, so before you complain, it's old data. It was not the most powerful processor, so it's historic data. I tried to give you an update on the processors. So I checked the internet for benchmarks, and I took the top scorer on the benchmarks. And I just assumed it will go linear with the comparison of the old processor or GPU. It's not real, it's extrapolated. But if this would be the case, you see like 64-core Ryzen could process a much higher bandwidth, but still runs at 280 watts. The GPU did not improve as much, and then still the FrankRubber, the most recent one, in terms of efficiency, it's still the best. So we can process in the moment 1.25 gigabyte a second, and hopefully in a few weeks we can double it to 2.5. Still work in progress. And again, it's the FrankRubber you may have anyway in your system. 10 Crabbers, whatever your main board or your Thunderbolt or whatever can cover, you add them to your computer. Now, talking about R&D, because I want to present like 2 projects. We had also a bachelor thesis in the recent weeks, finished I think 1.5 weeks ago. Photometric stereo only works on diffusive materials. When it comes to very shiny reflective material, it doesn't work. Glass, polished metal, doesn't work. So in this, there's the technology called phase measuring deflectometry, and what you need is like a sinus pattern generator with moving sinus. And then you see the screen, the pattern on your reflective surface, and by shifting it 4 times, you can calculate again the surface. Based on the bachelor thesis, we made this demo unit. It's a prototype. It's a bachelor thesis. For a bachelor thesis, it's amazing, but it's not a product. So don't ask me how much it is and what it can do. It's a bachelor thesis. And it's designed for line scan applications, but here on the Vision Show, we show it on the Matrix camera running at 1 kilohertz. And then you see it's a shiny material. It's a USB dongle from CodeMeter, shiny surface on the top right, taken by the cell phone, and the lower right, you see the image which we calculate inside the FPGA. And it's, this is like a test case if there's interest in the technology. So if you're interested in the technology, you can come to us, to our booth, and we can discuss what we can do and what we cannot do. So this is the first R&D project, and then also my last slide. We are working on our, we call it hybrid image processing. It's a public funded project together with Karlsruhe Institute of Technology and together with Basler. And it's, again, our strategy to move as much workload as possible to the FPGA, and we have a complete toolbox like based on multi-channel, photometric stereo, multispectral, in future maybe deflectometry. And we also have technology for high-speed sorting. So we have extremely fast solution with very easy algorithms which can process like 1 million granules a second, response time down to 1 millisecond. It's in the moment the technology we had is very fast but very stupid. So we wanted to have this technology being more smart. So we combined it with neural networks. So on our booth, you see free-fall sorting, where the decision is taken by a neural network. And here you see the concept. So we have like the frame grabber acquiring the images from the camera and from different line lights. And then the data is going back to the FPGA. It's transferred either in full resolution or just the cutouts, the blob, to the CPU or GPU, and then there's the inference or a high-level algorithm running in the GPU or CPU. The result is returned back at the high accuracy, and then we shoot them out of the air. And on the bottom, you also see this contact image sensor, the CIS, because you also see this on our booth. I explained the shape from shading technology, and company Tishava Vision has also a shape from shading sys, and we can acquire the images from this contact image sensor and also process the data, so you can have the full bandwidth of the sensor shape from shading calculated in our FPGA. So thanks for your patience. Drop by at our booth, yeah, and give us a visit. It's still a few hours to go on the last day. I'm happy to see you on our booth. Any questions?
Stelz, everybody, from MST Vision, correct?
Yes.
So do you have questions? Any questions? I have one question. I have heard this thing again and again in the last 3 days, that reflective surfaces are tricky.
Yes.
Why is that? I'm coming from a different perspective. I'm looking at the machine vision system from a completely different perspective, so I really don't have any idea about these
Me neither.
challenges.
So, I try. no, if it's a diffusive surface, let's say laser triangulation. You just need a laser, you see the laser light, and no matter where you put the laser and the camera, you see the reflection. If it's very shiny, it needs to be a V angle. So the cameras look at the surface and incoming angle, outcoming angle. So you need to have light coming from the direction. So it's very complex, because if you have strong topography, you need to have a large screen. And that makes it difficult. And large screens with a big area also need a lot of light. And then if you have like a screen, like pattern projection, yeah, it needs to be switchable in a very fast way, being still very bright, which is not easy. So laser triangulation can be a very powerful laser on paper, and wherever you put the camera, you still see the laser.
Okay.
And if it's reflective one, you need to put the camera to use your surface as a mirror to see your pattern generator.
And does it also work if the reflective surface itself also has some patterns on it?
Exactly. Yeah, because that's what you want to see, the pattern.
Yes.
So you want to see again the surface normal vector, because it's tilting the surface, and then your camera is watching at a different position on the screen. That's like deflectometry.
Okay.
Or you need a special sensor, like a point sensor, measuring the reflectance. Time of flight doesn't work on reflective surfaces because there's no light coming back.
I was just curious, because I heard it again and again in the last days, that everyone wants to compete in the reflective surface space, and how competitive we can do it.
Again, it's shiny materials, it's glass, it's the battery foil, it's very shiny. So there are a lot of applications which are shiny.
Perfect. Thank you so much.